Hey everybody, my name is Chris and I'm a tutor here at Chegg.com, and I mostly do math and a little bit of computer science. And in this video I want to talk about algebraic combinations of functions. So mostly what we're going to talk about is just some notational issues, and we're going to talk about what the domains of these four types of combinations are, and then we'll do an example of something that's a little bit tricky, so just so we can point out some things that we need to be aware of. So anyway, before we move on, let's go ahead and just make something easy on ourselves. Let's say S is the domain of f. And remember, the domain of a function is the set of all the values of x where the function is actually defined. Okay, so S is the domain of f, and then we'll say T is the domain of G. All right, just so that we can say S and T instead of domain of f, domain of G, domain of f, domain of G, and so we don't have to write that down all the time. So now, notationally, f plus g of x is just the same thing as f of x plus g of x. So basically, what this really means mathematically is that we can take a function f of x, add it to a function g of x, and then we will get an entirely new function that's just basically we can treat it as one complete function. Okay, because this is a function, this is another function, so we really have two functions here. But what this equation is saying is that we can really think of those two functions when we add them together as just one complete function. Okay, that's all that's really saying. So notationally, that's exactly what this means. F plus g of x is f of x plus g of x. All right, and similarly, pretty much almost identically, f minus g of x is just f of x minus g of x. Okay, so really nothing tricky going on here, nothing tricky, nothing weird or strange like that. It's just notational stuff here. And then, similar to both of these, fg of x is just f of x times g of x. All right? Now, before we move on to f divided by g of x, let's talk about domains. So what is the domain of f plus g of x, or f minus g of x, or f times g of x? Well, so let's just look at these one at a time. In order for f plus g to even make sense, both f of x and g of x have to be defined. Okay, so we need to have some value of x such that f of x and g of x are both defined. So in other words, the domain, if something is in the domain of f plus g here, then it better be in the domain of both this function f and this function g. So basically what that means, essentially, is that the domain of f plus g is actually s intersected with t, because s intersect t, that's the set of everything that's in both this and this. But if we want something to be in the domain of this, then it has to be in both this and this, okay? So basically, if something is in the domain of f plus g, then it has to be in s intersect t, because it has to be in both s and t. Otherwise, it's just not going to work. Okay, so, and again, the reason is that because to even make sense of f plus g, f of x and g of x have to both be defined. Therefore, the domain of f plus g is s intersected with t, as we have written down here. So let's maybe use a different color. So the first, well, before we write anything else, the same exact thing is true of f minus g, okay? So to even make sense of f minus g, f of x and g of x both have to be defined, okay? And the same thing with f times g. To even make sense of that at all, f of x and g of x both have to be defined. Otherwise, it doesn't even make sense for us to talk about f of x times g of x. So for these first three, actually, for f plus g of x, for f plus g of x and f minus g of x, and f times g of x, the domain is s intersected with t. So in other words, the domain is the domain of f intersected with the domain of g. Okay, because whatever this x is, it has to be in the domain of f and g in order for this to even make sense. Okay, so what about f divided by g of x? Let's move on to that one now. Well, this one, notationally, nothing really weird going on here. We just have f of x divided by g of x. Okay, so. And the same thing is true here, right? In order for this to even make sense, we have to have f of x and g of x. Both of these need to be defined. So the domain is going to be not quite s intersected with t, because since we're dividing now, we have an additional restriction that g of x is not allowed to be 0. Okay, so let's go ahead and make a note of that. So same with, so for f plus g, f minus g, and f times g, the domain is s intersected with t. Same with f divided by g of x, with the additional restriction, let's fix that, with the additional restriction that g of x is not allowed to equal 0. Okay, so just get rid of that here. So for f plus g, f minus g, and f times g, the domain is s intersected with t, and it's the same with f divided by g, with the additional restriction, g of x is not allowed to be 0. Okay, so let's go ahead and go to page 2 and work on that tricky example that we talked about. So let's say we have f of x equals x, and g of x equals 1 over x. Okay, now what is f divided by g of x? Let's fix that. All right, so f divided by g of x is what? Well, if we remember our notation here, f divided by g of x just means f of x divided by g of x, right? So let's go ahead and do that. So we're going to have, this is just equal to f of x divided by g of x, which is x divided by 1 over x. And if we divide by 1 over x, what are we really doing? We're actually multiplying by x, because remember, if you divide by a fraction, multiply by its reciprocal. So this is x times the reciprocal of 1 over x, which is just x. And of course, this is just x squared. Okay? So what we see then is that f divided by g of x equals x squared. All right, now that wasn't too bad, right? But here's the tricky part. What's the domain? What's the domain of this? Now, we want to be very, very careful, because we might be tempted to just look at this and say, oh, well, it's just plain old x squared, so the domain is going to be all real numbers. And that's not quite right, because remember, the domain of f divided by g is the same as in s intersect t, with the additional restriction that g of x cannot be 0, okay, because we're dividing by g of x. Now, if we go back here, so we want to make sure that g of x cannot be 0. Can g of x ever be 0? Well, no, 1 over x is already never equal to 0 anyway for any x, so that's not the issue. But the issue is that the domain of g of x itself, okay, if we look at g of x, the domain of g of x itself, what is the domain of g? Domain of g is all x not equal to 0, right? X is not allowed to be 0, because if x is 0 in g, then we have 1 over 0, which is totally not allowed, okay? And what's the domain of f? Domain of f is all real numbers. So the domain of f actually doesn't give us any restriction that we need to pay attention to. So the only thing that's really important here is the domain of g, because for the domain of g, we do have a restriction. Now, why is that important? Because again, remember, for all 4 of these, the domain is going to be s intersected with t, the domain of f intersected with the domain of g. But for this 4th one, for the division, we do have that extra restriction, so I do want to point that out. Now, for this tricky example we're looking at, the extra restriction is not the issue, but the issue is that there's a real subtlety here where the domain of g is giving us a restriction, which isn't really obvious from the final answer of f divided by g, right? Because when we do f divided by g, it simplifies, and we just have x squared in the end. Okay, so again, we might just be tempted to say, oh, because it's x squared, we're fine with all real numbers, everything's okay. But we're not, because we have this 1 over x here. So the domain of f divided by g of x is actually all x not equal to 0. Okay, so in interval notation, that would be minus infinity to 0, union 0 to positive infinity. That's how we would write that in interval notation. Now, you might be wondering, well, hey, since we ended up with x squared, why does it even matter what happens over here? And the reason is that because, well, you know, yeah, if you were given x squared right from the start, then you can just say, oh, x squared, all real numbers are fine, that's totally fine. But we weren't given x squared from the start, we were given this from the start, and we had to use this, and we had to use this to get to x squared. So if we're going to do that, then we better make sure that all the values of x that we have are legitimate. Okay, so since we have to use this and this, then we better make sure that both this and this are always defined. And this is okay, it's just x. But this one right here, if we want to make sure that this is always defined, then we better make sure that x is not 0. Right? So that's why we have to restrict 0 from the domain of f divided by g. Even though it looks like we don't because of the simplification, but we still do. All right, so this has been an example of finding the domain of a quotient function. And before that, we also talked about algebraic combinations of functions in general and their domains. So I hope you found this video helpful, and thank you for watching.